Okay, so we'll make a start. Thank you for coming. 5 o'clock Thursday. Most of your friends have gone. So I didn't expect more than 20. How many of you are here? 4, 6, 7, 8, 11, 12, 15, 18, 19. Okay, so including me. Okay, 20. So there you are. 21. Okay. So what I'm going to do is, first of all, the assessment that you did, I'm sorry for the delay. You'll get it tomorrow, definitely, the marks for the final assessment. So I'll make sure that I complete that tonight and give you the marks. So tomorrow you'll get that marks. And then I'll also send couple of emails about the tutorial session and the Zoom session that we may have for you to ask any queries. So related to your exam or anything else that you didn't understand or you want me to explain further, so that will be open to all. So just enter to the Zoom through your university email. Yeah. That I haven't decided yet, so at least one would be this side of the break, so that you can join from anywhere, and couple of those sessions at least in the new year, so that before your exam, and then I'll see if you need more, I'll probably put in more in that way. So it all depends on how many I'm getting. Yes. That's a good question. So at least this one, what I'll do is, considering people are probably all over the world due to the break, so I'll probably put the first one during midday UK time, the first one next week, so that people other parts of the world can join maybe, and then the following one in the January, probably I'll put one in the early morning, one in the late afternoon or something. So but the first one next week would be during the midday. Yeah? Is that okay, midday?
Okay, so it's going to be on the 23rd of December?
Not 23rd. So next Monday is what? 20th, right?
Yes. 20th.
So either Monday or Tuesday, I'll have the first session. Okay. So you can ask me. So it will be open. You can ask me any questions you like, and then we'll discuss that. And you can use the share screen as well. So if you've got a particular problem, you can share screen. You have the facility to do that, and then we'll see how it goes. Okay. And if we see that we require more sessions for your understanding, then I can extend that as a tutorial in that way. Okay. So now what you are at a stage now. Now you have, for these 4 assessments, I know it was okay, different way, but one advantage surely that you have gone through whole material because of those 4 assessments. So you know what it involves in structures 1. So you can have some, so you will not see things for the first time. For maybe for other units, you will start revising for the first time. This one you have already revised and have gone through. So now your questions would be much more in-depth and much more thought about and considered. So right time to give that sort of a tutorial where you'll asking, I'm sure you'll be asking good questions. In that way, it benefits everybody. But as I say all the time, that feel free to ask anything, because the things you think that you are not getting, maybe the other people are also not getting. So I'm going to first of all show you few apps for you to have a look at that. Some of these apps are also in the Android platform. This is I'm going to show you in iPad, but some of these apps are also available in Android, and also there are few on the PC or the Windows platform. So they're all, most of them are all free, or maybe some 89 pence or something, but most of them are free. So I'm going to show you few. So first one I'm going to show you is this one. This one is from a German one, and if I show you how they do that, so they will ask you to quickly say the axial force, they will call it by N, shear force by Q, and M for bending moment. And the sign convention they will be using is something, they have got a negative face and the positive face, but this is essentially the sign convention, which you could see the tension is the same as ours, shear force is opposite to what we have done, and bending moment is opposite to what we have done, but they do plot the bending moment on the tension face. So the bending moment they will be drawing on the tension face. So the shear force here would be opposite directions for us. And pressure over the whole bar in as minus, so that would be over the top in that sense on the compression face. And external force, these are the way. So how that looks like. So they give you score whether you can quickly do it or not. So if I start, for example, here, so you have got an axial force, and then that is asking for Q. Q is the shear force. Now, of course, this force will not create a shear force, so that is the answer in the middle. Second one is asking about, there is a moment, and then asking about the Q, shear force. Now, this moment will create reaction forces, one going up, one going down. So this is a clockwise moment applied. So the reaction force would be counterclockwise. So left side would be go down and right side will go up. So most likely you will get, now of course the shear force is not zero, so it is not the first. Second one is a candidate, and third one, shear force is not going to change here because there is no load. So the second one is the correct one. The third one is asking about bending moment. Now the load on to the right here, which is in the axial, that is not going to create any bending moment. Whereas this load will create a bending moment. And if you draw on the tension force, tension side, so the top side will be under tension. Now I think they do tension side, they mean the dotted line is the tension side they mean. So possibly this is the bending moment, the second one. I think this one is a bit funny. They say tension side is in the dotted line for some convention. Okay, no, the other one. Oh, game over. So if you make a mistake, they will game over. So okay, go by that again. So then axial force for this case, now it will have an axial force in this direction, but from this point onwards. And the roller will not have axial force, so this is the correct one. Moment at the end and creating a shear force. Now this is a cantilever beam. So it will be balanced by equal and opposite moment at the other side. So no shear force would be acting in this case. So the second one is the right one. Third one is again the asking for moment due to a force going in this direction. So the bending moment is 0. So that's the one. This is for the axial load. Now axial load is going in this direction, N. So that's the answer. Again, it is asking about axial force for this moment. There will be no axial force. And then the moment is, of course, the constant moment in this case, because moment will not vary in this cantilever beam. So you will put that one. So once you do that, then they will say, okay, you go on to the next level. So the next level, they will give problem gets a little bit complicated. So you'll have a triangular load, and you'll asking to get a bending moment, for example. So it will be tension side is at the top. So definitely this one is the correct one. there is a simply supported case with this, and it asks for an axial force diagram. Of course, the moment doesn't create any axial force. So, of course, that would be the, oh. What is this one? Just 1 second. Reaction forces 0. Was it N? Oh, yes, sorry. Yes, I don't know whether some of you plotted that, because this moment will create two forces in the opposite direction, and that would have a component in the axial direction. Yes, good problem. Good one. But if you, a problem with this one is if you make a mistake, you have to start again. Okay. So play with that. That is quite quickly you can get through this. So that's one type of problem. Other type is there is one called I-beam. Now this is quite good if you have got a problem and you want to check your answer, for example. So there are few types of standard problem. So point load, uniform load, partially uniform load, and say, for example, if it is a point load, you can put that one over here and say how much is the value of the load. Let's say you put it at 10 kilonewton, for example. And then you can say what distance they act. So maybe they act as, so total is 4, let's say 2.5 meter, for example. And the span, you can say, okay, span is, say, 7 meter. So then your shear force diagram is given, the reaction force is given, shear force diagram given, bending moment is given in kilonewton meter, and also the deflection in millimeter is given. Of course, the properties of the beam are given in here, that the material is modulus of elasticity is this much, and geometric constants like cross-sectional area, second moment of area is given. So if you have got a different second moment of area, you can put it in there, and that, so you can change those things over here. And also partial uniform load, if you want to do, then you can say for how for what is the value of the load. Let's say you can say this is 10 kilonewton per meter, and that acts over, let's say 1 point, or rather let's say 2.5 meter. 2.5 meter, and then that would draw the reaction force, shear force as moment diagram, maximum moment, as well as the displacement. So these are standard. Now we haven't done the third and fourth lot. You really cannot do as such. Possibly you can do third one. Third one, what you can do is you can analyze this by using what is called a superposition theorem. So what you can consider this as a cantilever beam, that means get rid of that support and find out what is the deflection at the other end, at the free end. And then you put a load upward, a reaction force, and find out what would be the displacement at that point. Equate those two, you will get the reaction force. Okay? So that is the way to do that. So you wouldn't know these reaction forces automatically, because here they gives you 15.8, 9.8, 11.7. So these three are reaction forces, and you have got essentially for a beam two equilibrium equations, summation of vertical forces 0 and moment about a point 0. You don't have the third equilibrium equation being useful. Third equilibrium equation is summation of horizontal forces 0. Now, as there is no horizontal force here, that is meaningless. So you have got two equilibrium equation and three unknown reaction, two at the left hand end, one vertical reaction, one moment, and one at the right hand end. Now you cannot find three unknowns from two equations. So this is statically indeterminate problem. So for this problem, if you want to solve this problem, what you have to do is as follows. So what you need to do is maybe I can put that one to that way. What's happened? Okay, so what you have to do is, in this case, you have to make this problem into two parts. So if you drew the free body diagram of this beam, why the middle one is still not working? Okay. This is the wrong thing to do, but anyway, let's see whether it comes back or not. That screen has gone blank. Sorry, just 1 second. Okay, hopefully. Sorry, just give me a couple of minutes. Okay. So what you need to do is, in this case, you have got three reaction forces. So reaction force 1, reaction force 2, and a reaction force 3, which is the moment, and of course you have got the load. So, but in terms of the equation, you have only two: summation of vertical forces 0 and moment about a point 0. So you cannot solve for this R1, R2 and R3 in this case. So what you have to do in this case is make this problem into two parts. So what you need to do is, first part, you have this beam and you have got this load, and then you assume this is a fixed one. So you have got, say, let's say something R3, and let's say R4. So you can find for this load what will be the deflection at this point. And then you take another problem, which is exactly the same thing over here. And then you put, of course, this side is also reaction force would be there. Now you put another load in these directions, which is form of the reaction. So it will go like that. So you find this one. So this is the delta 1 and this is delta 2. Now at this point, let's say this reaction force is R. So this point there is no net deflection. So delta 1 will be equal to delta 2. So that is the third condition. So this is the first, this is the second, and that is the third condition. And you have got three unknown, R1, R2, and R3. So you'll be able to find that R. I probably shouldn't say R, don't give the name. You could say this is fixed in this case. So any problem like this you get is called statically indeterminate problem. So the way to solve them is to start with a statically determinate problem, which is this, plus any unknown reactions that is there, so you put that in. Then you'll find, so you find the displacement from there, and you find the displacement from there. Then you equate those two, that will give you this reaction force that you need. Yeah?
Why don't we consider the load for the second case?
Because we are doing what is called superposition. So we are considering this is the basic beam, and basic beam, so this is called propped cantilever. So we're considering, okay, it is a cantilever beam. It has got a load plus this force. So let me explain that another time. So you have got this as the load, and if you consider a free body diagram, then this is also reaction force is another type of load. So what you don't know what it is. You know this is F, or here it is given as 25. So you know this is 25, but you don't know what is this. So how do you know that? You know another condition, which is at this point displacement is 0. So you know this point displacement is 0. So what you can do? You can break up this problem into two parts. You can say, okay, I'll have put my 25 load, and I'll find out, so this beam will deflect, I'll find out how much displacement is at that point. Okay? And then you put it in the second beam, and you say, now I'll put this reaction force, let's say R, and this will deflect in this way, so you'll have this displacement. So this is delta 1 and delta 2. Now this point delta is 0, so delta 1 must be equal to delta 2. So that will give you the value of R. So you will learn about this way, this type of problem solving in your second year, which is called statically indeterminate structure. Okay. Oh, another again gone. This is really not.
Do we have such a problem on the exam? Aesthetically
No. In the exam, you will not get anything that we haven't done. Okay, so that bit is absolutely correct. 9319. Okay, so I'll show you a couple of more. Okay, so that is so you can do. In fact, you can try using this one. Say, let's say this is 4 and this is 3. Let's say, okay, 4 and 3. So 4 meter and 3 meter was the load. So if you take that one and 4 and 3 exactly, and you find out what is the displacement. Displacement is 4.22, right, at the tip. Now go to that problem now, and you put in 25 exactly for the same. Now you can say, okay, 25 is acting upwards, or you can say the displacement will be up. So that is 6.67, for example. So that means this reaction force is in ratio of those two. So definitely less than 25. So if you go back to this point, you'll see the reaction force is 15.8, which will be in the ratio of 4.22 and 6.67. So you can use those expressions as well. Okay, so that's another problem from there. But what else I have got? So there is also another thing called similar, this beam HPC, exactly similar thing. Make sure you use units as SI, and you can change this I value, and that is too low, so probably 500. Yeah. So you can put this load anywhere you like, and that boundary condition, the support condition, let's say it should be 0, so that the left side, so that's the support conditions. And you can put you can put triangular load, which the previous one didn't. So you can put a triangular load in this case, and then the left side you can say, delete that load, delete that load. Okay. So yeah. So left distance location is 0, and the load value is, say, put it as 0. And then 10 is minus 1. Let's put that as minus 10, let's say. So that would be a triangular load, and then you can analyze, you can see the deflections, rotations, moment, shear force. Again, this is with the different sign convention it uses. So now if you want to delete that you can delete. So this is purely due to the triangular load. You can put a trapezoidal load, for example. So instead of putting 0.0, if you put this side, let's say minus 2, for example, or minus 3. So it would be a trapezoidal load. You can put that in the middle of the beam as well. So left location, if you say go from 2 meter to 7 meter, for example, then you can get a trapezoidal load as well. So my point of showing this is that when you are doing problems, sometimes another problem from somewhere else and you are not sure about the answers, then these apps will be extremely useful to check your answers. Yeah? So you can easily put that in and get your answers for this simple problem. So of course the answers for our problems are there, but you can check for other cases. And this gives you displacement and rotations, everything in here as well. So, and then that gives you a little bit about how to do that. And the final one I'm going to show you is something called sketchalyze. Here you can draw any standard frame that you like. So here you can draw a frame. So you can say, okay, not very responsive. Let me try that with another one. So here you can draw any structure. Let's say you can draw a 4 meter by another one. Say the problem we did last time, and then you put a support, let's say fixed support at that point, and you put a load, say concentrated force at this point, and give a value, let's say 10 or something. So, and you can change the direction of it and then use the computation. So axial force diagram, this load will create axial force only at the top one, shear force only on the vertical one, moment diagram, deformation, this is going to deform in this way. You can get idea of the reaction force as well. Now if you want to change the say let's say moment diagram, if you want to change the directions of the load, for example, so the load, let's say you want is a vertically downward, let's say 90 degree. You have to check which direction that, so that's upward, let's say downward 90 degree. Okay, so you put this load vertically downward, then of course your axial force diagram would change. Only the vertical one will have axial force. Shear force will be only on that top beam, and moment will be only at the horizontal one. And deformation diagram would look like that, and reaction force. So you can set up, and if you want to make this one little bit more complicated, for example, these are not very good. So if you say delete, yeah, so now you can say okay, and if you want to make a little bit more complicated like that, and then you put a load, let's say uniformly distributed load over this one with a Q for let's say 5 kilonewton per meter, and let's say you put another concentrated load at this point with minus 90 degree, so that goes downward with a force of 10 kilonewton per meter, and you put a moment at this corner, not that one, so you put a concentrated moment at this point, let's say counterclockwise, so minus 10. So now you can draw all sorts of things here. Axial force diagram, this will not have any axial force. You can put a shear force diagram. You can put bending moment diagram. Now bending moment will be continuous around the corner. So if it is 40 there, 40 would be there as well. And it would be like a parabolic curve. And then again here it is it is 10 times 3, so 30. So it will be 30 in there as well. And this would be the deformation diagram, reaction force as in there. So this type of one, simple one, would give you idea about how to deal with simple problems that you are dealing with it. And then other things, there is something called this will give you the equations as well. You can do a sections, for example, and the other stuff. Okay. So that's it really, and then what is that? That's it. Okay, fine. Sketchalize. Yeah. Louder, please. I couldn't hear it.
So the example that you just did on the strength master PhD, why did like some of the beams, like when you have the definition of them connected together, only the first one like went curvy and the other two were still straight?
So the corner joints will be always at 90 degrees. So when you mean the frame one, right?
Yeah.
Frame one
Only
would
the first
bend,
one. Yeah.
but they will not get in the positions, but they maintain 90 degree one. So
How
if
come they don't go all like bendy and curvy too?
yeah, so if I let me do one so that if I can capture your thoughts in here. Say if you have got a frame like this and you have got a load like that, for example, then this is going to bend, so it will bend and then it will maintain 90 degree there, and this will bend like that.
Oh, so it was just the simulation maybe didn't fully
Yeah,
understand.
so the simulation is not that one, but it will bend in that way. Yeah.
Can we solve a triangular load question?
On this one,
No, not like in general, like any question. Like
a triangular load on a beam.
Yes.
Yeah, why not?
In general.
So, any suggestions of the beam type, simply supported or
Simply supported.
simply supported beam?
Could you do a McCoy bracket of the triangle load of a simply supported beam or not?
Yeah, you can, of course you can. So, simply supported and triangular load over the whole
No, like one section, like maybe on the middle.
in the middle.
Yeah.
Okay, let's say this is 2 meter, 2 meter, and 2 meter. And what is the intensity of this load?
18.
This is 18.
Yes.
So 18 kilonewton per meter. Okay, that's good. So the first thing, before you do anything, you need to find the reaction forces. So there would be reaction forces here. So R1, and of course there would be a horizontal reaction force, but that's 0 because the forces are not acting. Yeah?
Oh, I know just about the 18 kilonewtons per meter.
Yeah?
So then, I think this is supposed to be concentrated down to a single point load at 4/3 of a meter away from the 2 meter segment.
Yeah, absolutely. So find out the total load. So the total load from there is, it's a triangular load. So it would be half 18 times 2. So the total load is 18 kilonewton. And where this will act? This will act 1/3 from this side and 2/3 from this side. So this would act at a distance here, which is, this distance is 2/3 meter. Okay? So how can you find R1 and R2? So take moment about point A. Moment about point A equal to 0 if you do. So you have got the load 18 kilonewton. So 18 times what is the distance? So if this is 2/3, that is 4/3. So this total distance, so this load will act at a distance 2 plus 4/3. So 2/3, this is 2 meter, is divided into 2/3, and this is 2/3 of 2 meter.
But isn't it like 1/3 from the...
1/3 from the side.
But why did you write 2/3 then, instead of 1/3?
So because this distance is 2 meter. So if this distance is d, this is d/3. So this was 2 meter. So that is 2/3. Okay? So this is 2 plus 4/3. So 18 times 2 plus 4/3, that is going to create a clockwise moment. That must be balanced by this R2 times 6 meter. So minus R2 times 6 equal to 0. So that will give you your value of R2. Once you get that, take it off from 18, that will give you R1.
The shear force diagram and bending moment diagram is clearly doing involve Macaulay brackets, right?
If you want to find out a general expression, if you want to calculate deflection, yes, that is easiest way to do. But if you are just interested in the bending moment distribution, then you don't need to use Macaulay's bracket.
I mean, Macaulay brackets can work for any function, right?
Yeah.
So as long as the value of the function so as long as the value of the result of the function with the x variable plugged in is less than 0, it doesn't work.
It doesn't work. So it's a switched off, that macro.
So basically, it's only switched off if the result of the value is less than 0. So for a Macaulay bracket, from a quadratic formula, it's going to be 0. It's going to be 0 when.
So this would be the reaction would be reaction R times X, and this triangular load only will come into force for X greater than 2 meter. Yeah? And then of course you have to consider this one if you are doing macular bracket, that is going like this, and an opposite force like that way.
Yeah, we're going to need to use Macaulay brackets.
Yeah. Yeah. Go on.
Also, there's speed.
Yeah.
Is there any way, like, to show
I cannot hear. Sorry.
is there any way to show us a quadratically distributed load?
Quadratically distributed load.
Yeah, I was trying to look.
Okay. So for example, let's say you have got a load like that. Is that what you are saying? Yeah. So first of all, you need to find out what is the total load. Now, of course, from calculus you know that if you have got a function, say function is say x times y, let's say I've got a function y equal to x to the power n. Then integration of that function is equal to, so x to the power n dx would give you x to the power n plus 1 over n plus 1, plus of course some integrating constant. That's from calculus that you already know. So you can use the same functions over here. So when we say for a triangular load you make it half, that comes from basically in here. So if the triangular load means here, if the load is triangular, then y equal to some constant times x. So the power of n here is equal to 1. So when you are doing the load calculations, so n equal to 1 means 1 over n plus 1 is 2. So that's why this half things comes in. And it is easier to show that when you take the moment or the centroid distance you do, then you do y times the x dx. So it is essentially x to the power n plus 1 dx. So that would give you x to the power n plus 2 divided by n plus 2 times c. So this is n plus 2. That means if n equal to 1 for triangle, it would be 1/3 of the distance. That's where its CG would be. So giving the same logic, so what I'm trying to say is, if a function goes like this, with y equal to x to the power n, then its area is x to the power n plus, in this case 1 over n plus 1 times this rectangle that it goes through. So let's say this height is h and that height is say b. So 1 over n plus 1 times b and h. Now how I am getting this b and h? That is, if you do the limit of x from 0 to that point, then that would give you this b and h. So if you have a curve y equal to x to the power n, then the area under the curve is, now one has to make sure that it goes from y equal to 0, x equal to 0. That area under the curve is 1 over n plus 1 b plus h. Check that here. So area under the curve, here n equal to 1 because that's a straight line. So that means half b times h, 18 times this distance. Now if it is parabolic, for example, so I use y equal to x square. Oh, sorry, another thing is the centroid distance in this case, if this distance is c, c is equal to 1 over n plus 2 times b. So that means b over 3 in this case. Now let's do this case, y equal to x square. If it is y equal to x square is the curve, then my n is equal to 2 now. So what is the area under the curve? Area under the curve, that means you need that for total load calculation, is 1 over n plus 1, which is 1 over 3, times the rectangle that it gives between the limit. So if this is h and this is b, then that is 1/3 b times h. What about the centroid distance? So centroid is here. So this distance, if it is c, so c is equal to, now it would be 1 over n plus 2. So 1/4 of b. So that's from calculus. Again, if you take it slightly further, if your load is cubic, for example, y equal to x cube. So if it is y equal to x cube, my n equal to 3 now. So the area under the load, which is this area, is say this is h and this is b. So my area would be 1/4 b times h. Yeah.
What if you like flip the curve, so instead of being like that, it was like
Yeah, that's the same way. So it goes from that. So here it would be 1/3 if this is y equal to x square.
instead of being like a scoop, it was like a hill.
Oh, then you need to deduct that. That's a very good point. So what you are saying is, so let me complete that. 1/3 a equal to 1/4 bh, and this distance, if it is c, so c would be 1/5 b. Okay, but your point is very good. So it is if the load on the beam is something like that, for example, you are saying. Yeah? So here what you have to do is, you have to do it in the two cases. So you consider this is the part that you know about, and then the rectangular part is the total, and then you deduct. Yeah?
So for a polynomial function, y equals to x to the power of n.
Yeah.
The area of the function when x equals to b, and x equals to b, and x and y n is equal, and y b is equal to h, is what exactly?
So if so you have to put in the limit from 0 to this part. So for x equal to when it is b, then that would be b to the power n plus 1, for example, and then you will get into these expressions here as well. So that would be h. Do you want me to show that quickly? The integration that you want me to show?
That integration is easy. Is it the integration of x, the integration of ax to the power of n?
Which bit you want to know? Oh, okay, I know where your confusion is. Say your confusion is here. I am drawing y equal to x to the power n. This is x and that is y, and I have got two limits. There is 0 and there is b, for example. So what is this value here? This value is, here it would be b to the power n. So b to the power n is nothing but I am calling it as h. So h is b to the power n. Is that okay? So now it's fine? Yeah, so how do I get that? So of course integration of y dx, limit is 0 to b, so that would be integration of x to the power n dx 0 to b. So x to the power n plus 1 by n plus 1 0 to b. So that would be b to the power n plus 1 divided by n plus 1. and minus 0 is this. So this one you can confirm as b to the power n times, sorry, b times b to the power n divided by n plus 1. So that would be b, and b to the power n is h. Is that okay for everybody? Does that answer your question here?
It does, yeah, but it's also like talking about the header.
Yeah, and if it is the other way around, you just do the equation that you know and flip it or deduct it from a rectangle.
So for the above case, for the hill type stuff, if we know the equation, then we can directly integrate it.
Absolutely. Absolutely. Okay, so please bring in questions like this or anything else from the, if something is not clear from the notes, from the examples, from the tutorial sheets, anything that is not clear, do bring us in the Zoom sessions next week. So I'll send you an email over the weekend, either whether it is Monday, what time, or Tuesday, what time. I'll try to get it on Monday sometimes for this, so so that you have got some more time. And the exam would be exactly very similar pattern that we have done for this online test. So for exams, you don't need to prepare as such very differently than what you have done. What you need to do is make sure that you take care of the units, take care of the signs and that sort of things. And other than that, it will be 2 hours. Yes.
Is it an online exam?
It will be online exam. It will be online exam in the computer cluster in this floor, and possibly one at the upper floor as well. So it will be in this building. Online, yeah. Online, but it in the computer cluster, not here. You can't use your own device. So you have to use the computer in the cluster. I have to discuss with the exam office. That's what I said. I'll come back to that. I don't have any problem for you to bring in books, but there are some invigilations rule for the universities. So I'll see that, and I'll send you an email towards that effect. But I personally don't mind if you want to bring your books, notes, because you have to bring in certain amount of papers to do the calculations anyway. So as it stands, my suggestions would be to the exam office for you to allow to have books. Only thing that they will be careful about